Hello everyone, once again welcome you all at Lokeser Unlimited Study Zone. So we are continuing with the chapter Magnetism and Material. So in last class we have completed a derivation related to the magnetic field intensity at axial position and at equatorial position. Now the intensity derivation, or you can say the magnetic field strength for a axial condition for a given bar magnet or a magnetic dipole is given by B equals to mu naught upon 4 pi multiplied by 2md divided by d square minus L square whole square, right? So now what is our concern? A special case is the case when there is a short bar magnet, or you can say when the dipole is small. Okay, bar magnet is small or dipole will be small. So when the dipole will be small, then what will happen? See here, this is a south pole and this is a north pole. If dipole is very small, this means this effective length will be very less. Comparison to this effective length, point, the external point at which we have to calculate our magnetic field intensity will be at a larger distance, right? Understood? So this means the distance d is quite larger than r. Sorry, not it is r, it is L. Okay? Because L is the semi length, or you can say half of the effective length, because the total length we considered as 2L, so it is half the length. Okay, so if D is very greater than L, then what about D square is very greater than L square, right? So D square minus L square can be written as it approximated as D square. Agree? We can approximate D square minus L square as D square. So I can put the value here, B equals to mu naught upon 4 pi. In the same derivation, the numerator was 2m into d and denominator d square minus L square whole square. And we have just approximated d square minus L square as d square. So in the place of d square minus square, we will put d square, again power 2, right? Now 2 into 2 becomes power 4. Multiply. So the next part of this derivation, mu naught upon 4 pi 2 md divided by d to the power 4, right? And numerator there is single d and here is 4. So 1d will cancel, each of the d will cancel from numerator and denominator. So 3d will be left out, okay? And the derivation will be b equals to mu naught upon 4 pi 2m by d cube. Clear? And direction is along n to p. Why? Because there is n pole, and from N to P, the field strength is higher. This is V1. And S to P is lesser, as the south pole is distant from this point P. Okay. So this is B2. So the net field will be given as B1 minus B2. Okay. So the direction of the net field will be from north to P, means N to P in forward direction. Clear? Yes. So note it down. So B equals to mu naught upon 4 pi into 2m by b cube. So important relationship develops here for the numerical, that b is inversely proportional to d cube for numericals. Okay, b is inversely proportional to d cube. Note it down. Now talking about when the point lies on equatorial line of the bar magnet. Okay, so for the equatorial line of the bar magnet, as the resultant field is going backward, you see this is the direction of resultant field. Okay, so what is concept, that in the case of axial line, the direction of resultant field is along with the direction of magnetic dipole moment, because direction of magnetic dipole moment is going from south to north, right? So in the case of axial condition, you can say and write this thing, that B axial is parallel with vector M. Vector M means magnetic dipole moment. Okay, that is going from south to north. Clear? So write this one. Biaxial vector form is parallel to vector M. And then second case, what happening you see here? The resultant field B is going toward left side and the magnetic dipole moment is going from south to north. Yes or no? Means B and magnetic field B and magnetic dipole moment capital M are anti-parallel. Okay. So here the direction will be opposite. So it is written here. The direction of B is opposite to vector M. Clear? So if you write this one is in vector form, then what will happen in vector form? I can write here. B vector is equals to mu naught upon 4 pi. Okay, derivation is equals to M upon D cube. And here it will be a negative sign. Okay. Negative sign reflect that the direction of magnetic field is just reverse the direction of magnetic dipole moment. Clear? And same thing will be happening here. If you're talking about this derivation, that how this came out. So let's see. Here the d square plus l square whole to the power 3 by 2. And talking for very short magnet, again d square plus l square. This thing, if l is very small, then this could be written as d square, right? D square plus L square can be written as D square. So eliminate here D square. So like mu naught upon 4 pi 2 into ml. This is the formula pole strength into magnetic length that becomes capital M. Now I write here B equal to mu naught upon 4 pi multiply by M. And here D square plus LA square equals to D square whole to the power 3 by 2. Now see 2 and 2 get cancelled out, right? So what we left? B equals to mu naught upon 4 pi multiplied by only m by d cube. Previously it was 2m by d cube and here it is m by d cube. Clear? Any problem? Yes. Note it. Okay, dealing the next case. Sometime it has been asked in the examination. When the point makes an angle theta with axis on a bar magnet. Clear? Listen, when point makes angle theta with axis on a bar magnet. So here it is a bar magnet and this is with vector capital M. Clear? This is vector capital M. Capital M vector means magnetic dipole strength. Okay. Now, if we consider a point here, this is the point P. This is the point P. Now, we have to find the magnetic field intensity at this point. Okay. So if this complete vector is vector M, now if you resolute this vector M in the direction theta, so the component in the direction of theta will be equal to M cos theta. Agree or not agree? Because if you have a given vector R and if you resolute the component of this vector R into perpendicular side, then the component in the direction of theta will be given as R cos theta, and that is this is called axial component and this is perpendicular component is called R sine theta, right? So if this is direction M, then this component equals to M cos theta. Clear? Now see, we have to find the intensity of magnetic field because of this M cos theta, right? We have to find the intensity of magnetic field because of this M cos theta. Now the point P, if we consider the point P in axial position of m cos theta, then the component will be first component. First component is act upon its axial direction, right? So it will be given B1 is equals to mu naught upon 4 pi into 2m cos theta by r cube. Why? Because the previous formula we have B1 equals to mu naught upon 4 pi into 2m by r cube. Okay, it was for the axial condition, but now we have not complete m. The component of m acting here is m cos theta. Clear? So first, this is the component B1, right? Second case is B2. Second case is B2. So second case B2 is equals to mu naught upon 4 pi, mu naught upon 4 pi m sine theta by r cube. This one part, B2. Okay, so B1 equals to 2m cos theta by r cube and B2 is equals to m sine theta upon r cube, right? Yes, so actually, why we taken m sine theta? So we have two components. One is m cos theta, that is in direction of theta, in direction of theta. And second component will be m cos theta. Second component will be m cos, sorry, m sine theta. I'm sorry. Yes, look here. This is m sine theta. I'm drawing it with the red color. So now m sine theta. Is it visible to you, m sine theta? Yes. So see, this is a full vector m, and in the direction of theta, this component is m cos theta, and perpendicular to this component at 90 degree, this is equals to m sine theta. Clear, beta? Now you know the complete angle between m cos theta and m sine theta is equals to 90 degree. That's why these are called rectangular components. In class 11th, you have studied these are called rectangular components. Clear? Now think, this point P is lying on axial condition with m cos theta. Agree? This point P is lying in the same axis of m cos theta. Agree? Yes or no? Huh. And this point P is lying on the perpendicular direction for m sine theta, because m sine theta going somewhere here. So it is just perpendicular on this. Agree or not agree? So B2 axial direction, B1 will break in axis and B2 is backside. So this is B2. So finally we have two component. For m cos theta, it will be B1 part is equals to mu naught upon 4 pi 2 times m cos theta by r cube, and B2 equals to mu naught upon 4 pi m sine theta by r cube. Done? Okay. So finally we have two components. Now by vector addition rule, we know if we have two vectors in perpendicular direction, so either by you can use Pythagoras theorem or vector rule. Okay, in class 11th you have must you have read out that r equals to a square plus b square, resultant vector. Yes or no? So this is a square. In the place of a, we have the component of b1 mu naught upon 4 pi 2m cos theta by r cube ka whole square. And here it is mu naught upon 4 pi m sine theta upon 4 pi. Sorry, mu naught upon 4 pi m sine theta upon r cube whole square. Clear? Now, if you solve it, then mu naught upon 4 pi, take the things which have perfect square. So mu naught upon 4 pi giving you perfect square from here, and mu naught upon 4 pi giving you perfect square from here. So you can take it out as a common. mu naught upon 4 pi. M will also here give you a perfect square. So M is also taken common. And R cube is also here in both the terms. So R cube taken as common, right? So the leftover part will be 4 times, because 2 ka square 4. 2 square will give you 4 cos square theta plus sin square theta. Now 4 cos square theta plus sin square theta may be written as, you can write it 3 cos square theta plus cos square theta plus sin square theta, right? Yes, so cos square theta plus sin square theta is identity. So it will be give you 1. So what is derivation? 1 plus 3 cos square theta. This is the resultant intensity. Okay. So guys, we have three formulas. First formula can give you intensity at only axial condition. Okay. In the axis of the magnet. In second formula, you can find the intensity at only equatorial condition, that is on perpendicular bisector. Equatorial means perpendicular bisector. But in the third formula, this is the generalized result. You can find your intensity anywhere. Done? So you can find your intensity anywhere. B equals to mu naught upon 4 pi m by r cube 1 plus 3 cos square theta under root. Okay? Like you can generalize. So this is general result for all the cases. How? Let us see. If you put theta is equals to 0 degree. If you put theta equal to 0 degree, this means your theta equals to 0 degree. Means reduce this angle. So if you reduce this angle, so this vector will lie upon this direction, and case will be arise for axial condition. Let's put the theta equal to 0 degree here. B equals to mu naught upon 4 pi. Nitin, this is m by r cube. Now see, this is 1. Okay, I can place here 1 plus 3 cos square 0. You know the value of cos 0 equal to 1. Cos 0 equal to 1. So 3 multiply with 1 will give you 3. So 3 1 ja 3. So answer 1 plus 3 equal to 4. And a square root of 4 will be give you 2. So B equals to mu naught upon 4 pi into 2 m by r cube. Agree? So does it give the same result that what we have derived for the axial condition? Yes or no? Yeah, it is giving the same result. Okay. It is B axial. You see, it is mu naught upon 4 pi 2m by d cube. Okay. D is the distance. Okay. So here the formula B equal to mu naught upon 4 pi 2m upon r cube. We have considered this distance r. That's why there is a slight change in the parameters. But if you consider it d, your result will be in the form of d cube. Okay. Any problem? Now for 90 degree, if you take 90 degree, yes, for perfectly equatorial condition, your angle will be equal to 90 degree. So put here 90. Cos 90 will become 0. Clear? Now cos 90 will become 0. So if cos 90 equal to 0, then formula will be mu naught upon 4 pi m upon r cube. You can also take d cube, no problem. These are just symbols. So mu naught upon 4 pi m by d cube. Under root of 1 will be left. So under root of 1 will be give you 1. So your answer will be B equal to mu naught upon 4 pi into m by d cube or r cube. This was the same result that we have derived for the equatorial condition, right? I mean to say this is general formula. You can apply anywhere this one. Okay. Okay. So please note it down. Next part of the derivation is direction of resultant intensity. Okay. Yes, students. See, if you have one vector is B1, that is in horizontal direction. Second vector is B2, that is perpendicular direction, right? So the resultant intensity is somewhat here as at an angle alpha from the base vector B1. Okay. Then you need to calculate the direction of the resultant vector. This is what? This is the resultant. You just have calculated r equals to B1 square plus B2 square. And now we want to find the direction of R, direction of resultant intensity. So if this angle is alpha, if you taking the tan of the alpha, all you know tan theta is equals to perpendicular upon base. Okay. For this angle alpha, what is perpendicular? This one. And by the parallelogram law, if this vector is B2, then the magnitude of this vector is also B2. And this is B1. Agree? So tan alpha is equals to B2 by B1. So in the same way here, tan alpha is equals to B2 by B1. See here, what is B2? B2 is the second part of intensity, that is equals to mu naught upon 4 pi m sine theta by r cube. So I can write tan alpha equals to B2 is the mu naught upon 4 pi multiplied by m sine theta upon r cube. Clear beta? And B1 equals to mu naught upon 4 pi, that is 2m cos theta by r cube. Let us check again. Here 2m cos theta by r cube. Exactly. So now mu naught upon 4 pi, mu naught upon 4 pi get cancelled out. R cube and r cube get cancelled. And m cancelled. Now tan alpha equals to 1 by 2. Numerator will be sine alpha and sine theta, and denominator will be cos theta, right? Sine upon cos theta is equals to tan theta. So 1 by 2 tan theta. Yeah, exactly. So tan alpha equals to 1 by 2 tan theta, right? So tan alpha equals to 1 by 2 tan theta. Okay. So this is the direction of resultant intensity. Okay. So make the topic direction of resultant. Direction of resultant. Clear? Okay. Note it down. Direction of resultant. Sure, any doubt? Direction of resultant. So write the heading bar magnet is equivalent to solenoid. This is we have a given solenoid. For an ideal solenoid, the number of turns should be large. Number of turns are called capital N. Total number of turns. Clear? The length of the solenoid is considered as a small l. The length of the solenoid is considered as a small l. So if L length contained n number of turns, if L length contained n number of turns, then unit length will contain n by L number of turns. This is called number of turns per unit length. Okay, number of turns per unit length, and commonly denoted by small n. Very important, n by L. This term is very useful. A small n equals to capital N by n L. Number of turns per unit length. Clear? A small n means number of turns per unit length. The number of turns in unit length. Okay. 1 meter of length containing how many terms? More will be the a small n, more will be the magnetism produced by the solenoid. Okay. So right here, small n equals to turns per unit length. Turns per unit length. Clear? Now see, if I connect a battery here, s- but battery could not be connected in this way. Yes, see, first we have to wrap this coil, this is core. This is called core. You can either take iron core, air core, plastic core, thermocol core, okay, upon your choice. So see, in from the back side, you will wrap the first turn, then second turn, then again third turn. Likewise, so many number of turns may be wrapped around this coil, around this core, is said to be core, okay? And this whole structure, and finally, the last turn will be coming out from here, and you have connected a battery. This is plus and minus, okay? Clear, beta? As you on the switch, this coil or this solenoid behave like a bar magnet. One of its end become north pole and one of its end become south pole. Okay. Now see, from the behind, the current is coming like this. It is the wire is going from behind and then front side going downward. This is the front face of the wire, and this is the back side of the wire. Can you imagine this? Now see, this is the direction, clockwise or anti-clockwise? This is clockwise. Okay. Clockwise or anti-clockwise? Clockwise. Current is rotating in clockwise way. So if you see this one from your eye, front of this section, then there is a clockwise movement of current. Yes, like this. So beta clockwise current will give rise to south pole. Okay. You can align these arrows. Sorry, this arrow will be upside. You can align these arrows. Okay. So according to the alignment of these arrows, this pole will be south. Clear, beta? Now, if this pole will be south, then here, if you see from here, if you look from here, then the direction of current will be anti-clockwise. Agree? Yeah. So anti-clockwise direction. Look, if in a circular loop, there is a flow of anti-clockwise current. So this is anti-clockwise current because here 12 o'clock and 3 o'clock, sorry, 9 o'clock. So if your watch is moving from 12 to 9, then it is moving anti-clockwise. Okay. So anti-clockwise. So look the arrow. Does these arrows support my north? This is north. Okay. These arrows support align in the direction of my north. So this is called north pole. So here it will develops the north pole. Clear? So now two poles are developed here, north and south. So because of development of two poles, this solenoid will behave as a bar magnet. Okay. So lines of forces will be continue to originate from north pole and moving through the south pole. Clear, beta? Once again, it is movement of lines of forces, magnetic lines of forces from north to south. And they are forming closed loop. As the definition of magnetic field says, that magnetic lines of forces are continuous closed loop traveling from north to south outside the magnet, and inside the magnet it is south to north. Okay. Yes, so in this way magnetic field will be continue. Magnetic field will be produced in a solenoid, and solenoid is equivalent to bar magnet. Clear? Any problem regarding this theory? Okay, one trick I can give you. If there is current is anti-clockwise, when you say the current is anti-clockwise, okay, anti-clockwise. So can you say this anti as anti? Look, this anti as anti, okay? So N means north. N means north, okay? So where there is anti-clockwise current, then this means there is the development of north pole in a loop. Clear? So NT means N means north. So there is a development of north pole. And where there is clockwise current, so there is a development of south pole. Done? Clear, beta? So this is all about bar magnet as equivalent to solenoid, or solenoid as equivalent to bar magnet. But remember, one thing is there. Here, the magnetic field will be continue till the current is flowing. When the switch is on, up to when the switch is on, the current will flow to continue. The flow of current is continue. Okay. As you switch off, as you switch off the circuit, switch off the key, then the current will be zero. Okay. And this magnetism is closed. Okay. No fluxes are there. No magnetic field will be there. It means this is a electrical based magnet. That's why solenoid is also called electromagnet. Okay. It is called electromagnet. In class 10th, we already have read this. This is called electromagnet. Okay. The magnet that is governed by electricity is called electromagnet. Clear? Yes. So when I equals to 0, this is the advantage of this magnet. Whenever I equals to 0, production of magnetic field equal to 0. When I equal to 0, then production of magnetic field surrounding the magnet, inside the magnet, this is equals to 0. Clear? Electromagnet. Now tell me, electromagnet is looking what type of magnet? Is it a permanent magnet or it is a temporary magnet? Tell me what type of magnet it is. It is permanent or temporary? Yes. The magnet that is coming from Earth, okay, that is a permanent magnet, north-south magnet. You can't wipe off the magnetic field of permanent magnet, okay? Everywhere you can see its magnetism. But here it is a temporary magnet, okay? Till you will flow the current, magnetism will be there, okay? As you just off the current, then magnetic field also zero. Clear? So it's a temporary magnet. One more advantage. Can you tell me one more advantage of this magnet, electromagnet over a permanent magnet? Or you can say over bar magnet? One advantage. Sure. Hmm. Any idea? No. Look, flux is directly proportional to current. Flux is directly proportional to current. So as you increase the current, the number of flux are also increases, or you can say on increasing the current, magnetic field is also increases. It means by applying more current, you can realize more magnetic field with the same electromagnet. Okay. In a bar magnet, you cannot increase it intensity or decrease it in intensity at a certain point because it is a fixed amount of magnetism. Yes or no? But in an electromagnet, by using the amount of current, by increasing current, you will have a stronger magnetism surrounding this. Clear? So this is the advantage of this solenoid or coil over a fixed magnet. Okay, you can increase its magnetism, you can decrease its magnetism as per your need. Okay, so this is the advantage of this electromagnet. Now talking about the magnetic field of this solenoid, so write the magnetic field of solenoid. B equals to mu naught upon 4 pi into 2m upon r cube. This is B for solenoid. Okay. You see, this is exactly same derivation, same result that we have derived for the axial condition magnet. See, B is equals to mu naught upon 4 pi 2m by r cube or d cube. Clear? Okay. So this is the same result. B equals to mu naught upon 4 pi 2m by r cube. Clear? Hmm. Now, one more thing is there. We have seen magnetic dipole moment for what? We have seen magnetic dipole moment for a bar magnet. That was m into 2l, a small m into 2l. देखिए, look, we have two poles having different polarity but same pole strength m. So if this is north south pole and this is north pole, then the magnetic dipole moment, that is directing from south to north, m vector is given by m equals to magnitude of this uh, quantity. Magnetic dipole moment is equals to small m multiplied by 2l. Clear, beta? This was the magnetic dipole moment for a bar magnet. Now, for a current loop, remember m equals to I multiplied by A. I means amount of current flowing by 1 ton and A means cross-sectional area. Clear, beta? So M equals to IA. Very, very important. Okay. So what will be the unit of magnetic dipole moment from here? I reflect ampere. The unit of I is ampere and unit of area is meter square. So beta यहाँ पे unit of M equals to ampere meter square. Capital M equals to ampere meter square. Clear? Now, as the current loop can have many tons, so if there is only 1 ton in a loop, it will carrying a current I. But if it contains 2 tons, then the current will be twice of I, right? So if there are n tons, so for n, number of n tons, answer m equals to n I a, right? For n tons, m equals to n I a. Clear? For n tons, m equal to n I a. And see, if there is a solenoid having length L, then what we have read, we have talked about a small n, that is number of turns per unit length, capital N by L equals to n. Okay. So in terms of a small n, I can write capital N equals to n into L. Yes or no? So M equals to, in the place of capital N, you can write the value of small n into L into I, and this is area, right? If you see these loops, these are the circular loops. For that, area equals to pi r square. Area equals to pi r square. So M equals to N L I pi r square. Clear? This is magnetic dipole moment for a solenoid. Look, yes. M equals to I N, okay, into L pi r square. This is considered the whole length capital L as a 2L. Okay, like this was a solenoid. Okay, so I have taken the full length as capital L. Okay, and according to the magnet, like a bar magnet, they have considered this one 2L. So that's why this 2L term is coming here. Okay, rest no difference is there. So M equals to N L I pi r square. Everything is there. N is there, L is there, I is there, pi r square is there. Look, N is there, 2L is there, I is there, and pi a square. Why r square? Actually, we have to take the radius as a. We have to take the radius as a because we have already taken r as a distance from the center of the that point, investigating point. Okay, so there may be confusion. Okay, so we have to take this radius as a. Clear? Okay, to avoid the confusion, we have to take the radius as small a. So the area will be pi a square. Okay, pi a square. Remember, in physics, your concept should be very clear. Okay, to avoid any type of confusion. Okay, so here radius is a, so it will be pi a square. Clear, beta? Now you can note this. So this is the derivation for magnetic dipole moment for a solenoid. Okay, so this is very important line for every current carrying loop. The magnetic dipole moment associated with a current carrying loop or current loop is equals to M equals to NIA. N is the number of turns, I multiplied by A. Okay, so write this line. This is very important. But one thing we have to rectify here. This should be capital M. Okay, because a small m is considered as a pole strength. So this is capital M. Capital M equals to capital N number of turns. I means current, A means area. Now, in vector form, right, also in vector form, capital M equals to N I multiplied by area vector. N I multiplied by area vector. Okay. So what is the difference? Try to understand this. In the case of bar magnet, we have considered the direction of magnetic dipole moment is south to north directly. Clear? But now we have given a circular loop and current is flowing like this. Okay. So what is this direction? Anti-clockwise. This is anti-clockwise. Clear? Now the direction of magnetic dipole moment will be here upward like this. So this is the direction of magnetic dipole moment. Why? Because magnetic dipole moment M is equals to, for n number of turns, it would be NIA, but only one single turn is here. So if current I is flowing through this coil, this loop, it would be IA. And area vector is always perpendicular to the plane of the area. Okay. The direction of area vector is always perpendicular to the plane of area. Direction of area vector is always perpendicular to the plane of area. You can write this direction of area vector capital A is always perpendicular. This is the symbol for perpendicular to the plane of that surface. Clear? Hmm. I want to give one more clarification, interesting clarification regarding this. Look here, this is a current carrying loop, and if you see it from the upside, then here it is in the upside. This is anti-clockwise movement of the coil, right? So from the front, it is looking here north pole. Yes or no? From the upside, it is north pole. Clear? But from the downside, it is south pole. Yes. If from the upside it is looking anti-clockwise, then from the below this coil, it will looking you clockwise. Yes or no? So the upper polarity is north and the lower polarity below the coil, it is south. Yes or no? And we know the magnetic dipole moment is directing from south to north. Yes or no? So it is going upward. Can you realize? Nitin, is it clear? The direction of magnetic dipole moment is going from south to north. Okay. So conceptually they are identical. In bar magnet's direction, the direction for magnetic dipole moment is south to north. And here it is also south to north. Clear? And you can also apply the right hand thumb rule. Yes. Align your finger curl in the direction of loop. Yes. See, this is your laptop screen. Okay. So align your finger in the direction of this curl. Okay. Curl your finger in the direction of loop. Right. Now point out where your thumb is going. Does your thumb is going upward? Yes. So your thumb will be give the direction of magnetic dipole moment. Clear? Very important. So M equals to IA. Magnetic dipole moment for a current carrying coil is given by M equals to IA. So finally, once again, write M equals to IA vector for N turns, M equals to N IA vector. Complete. Regarding the solenoid, one thing must you remember that the field inside a solenoid and outside a solenoid. Yes. So here the field outside the solenoid is non-uniform. Outside the field it is non-uniform. Okay. And if you have given ideal solenoid, then B outside is equals to 0. But when you have given ideal solenoid, yes. So for ideal solenoid, B outside equal to 0. Clear? But inside the solenoid, the magnetic field is uniform. Very important. Inside the solenoid, the field is uniform, and the value of this magnetic field, B vector, equals to, write the magnitude of B equals to mu naught Ni. Very important. B, okay, inside the solenoid. Okay, and this field is uniform. Clear? Uniform means intensity is everywhere is same. The intensity of magnetic field at each and every point will be same. So this is the formula for B inside mu naught Ni. Okay. And at the corner of the field, yes, corner of the solenoid, not field, at the corner, like these points. These are the corner point. Yes. End point. B and B and these are the end point of the solenoid. What is magnetic field? It is mu naught Ni by 2, just half of the field at center or field inside. Okay. Yes. B equals to mu naught Ni by 2. B and equals to mu naught Ni by 2. So here N, remember N equals to capital N by L and B is proportional to I. As you increase the amount of current, magnetic field will also be increases. Clear? So that's this, because of this reason solenoid become very useful to us as it behave like a electromagnet. You can increase up the intensity of magnetic field inside the magnet, inside the coil by increasing the current. Done.